The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
There's many reasons for going into ternary blends or quaternary blends or even five-way blends, whatever. I mean, the SCMs that we have available to us are all very different. Fly ash can be different itself. Like Class C fly ash to Class F fly ash, silica fume is different to slag. And there's many good reasons for blending these materials together. And I think Jan touched on some of the synergistic effects. And we particularly see synergism when we take a fast-reacting pozzolan, like silica fume or like metacholine, and we put it with a more slowly reacting material like fly ash or slag. We get the benefits of both materials. We get good early age performance, but we get later age performance too. And hopefully from these very old slides, I'm going to be able to demonstrate that. One of the first projects that I got involved in where ternary blends were actually used was in the CN rail tunnel that crosses from Sarnia to Port Huron, so it crosses from Ontario to Michigan. Now, this is a tunnel that goes through some very aggressive conditions, fairly high chloride levels. Actually, in the groundwater, there's a high chloride levels. It's quite close to the salt deposits in this area. A fairly high hydrostatic head on the tunnel itself as well, and sulfates in the groundwater as well. So it had a 100-year design life, and when the specification hit Ontario, it was pretty much the first time a diffusion coefficient ever appeared in a specification. In fact, I'm pretty sure this is the first diffusion coefficient specification in Canada. So this is somewhere in the mid-90s. Initially, nobody knew how to run a diffusion test at the time. The ASTM test was not, the 1556 test that I think Jan mentioned was not published. There really wasn't a published diffusion test available. So that made it complicated. Nobody knew how to calculate diffusion coefficients in Ontario at the time either. We had to send the data had to be sent back to England, which of course everyone knows is a font of all knowledge, and they calculated the diffusion coefficients there. Initially, all of this was ready-mix concrete. It was a ternary blend that was blended at the mixer. Initially, it was 8 or 9% silica fume. It was just a binary blend, and they cast about 2 weeks' worth of production just with a binary blend with 9% silica fume. And you'll notice there the diffusion coefficient, they were actually making the limit. The limit was 600 times 10 to the minus 15. They were making that quite comfortably, halving it, in fact, getting a diffusion coefficient at 120 days of about 300. They experienced microcracking in the concrete, and this was attributed to the silica fume for whatever reason. In the 90s, there was lots of discussion about silica fume showing strength regression. Probably some people remember that, causing microcracking. So they decided to solve it by moving to a ternary blend and putting 30% fly ash in the mix, and that's the mix they eventually used is the one that's shown there. They easily made the strength, and they just assumed they were going to make the diffusion coefficient. Now, this is a great example of a diffusion testing not being a good tool for quality control. And for a start, you had to basically cure the concrete for 28 days, then pond it in a chloride solution for 120 days, and then do your chloride profiling, then do the chemical analysis of all those samples, then send it to some highly paid consultant in the UK to calculate a diffusion coefficient. By the time you got the diffusion coefficient back, you'd already cast 500,000 of these tunnel lining segments, right? It was a little bit too late to find out, but it didn't meet the specification. And in fact, it didn't. It was just over the specification. That 750 value there is the value for the ternary blended stuff. Well, what do you do if you've got 750,000 tunnel lining segments that don't meet the specification? You build the tunnel with them. Fortunately, we were able to get specimens of this concrete, and we tested it over the years. And this shows some of the data that we collected between 2 and 15 years. And you can see that the mix they actually did use in the end for the bulk of these tunnel lining segments did meet the specification eventually. It was just a question of time. I'm showing the specification value there is the green triangle. The blue line is for 9% silica fume in the binary mix, and the ternary mix is shown there in the red. And this pretty much fits in with a lot of the theoretical data that we've developed and shown before. We're showing that with the fly ash in there, we don't get a very low early age diffusion coefficient, but it does catch up and it gets better with time. You can also see with a straight binary mix with straight silica fume, you're really not seeing an increase in performance with age. Pretty much you get what you get early on, and it doesn't get much better. And I think this slide here really highlights the importance of a ternary blend. Whether that third component is fly ash or slag, it's going to help you in the long term. Now, you might think if waiting for 15 years to get a really low diffusion coefficient is too long, but if you're designing something for 100 years, you really should know what's happening in the first 15 years. The use of the second SCM is really helping long term. We also tried to model this using Life 365. I'm not going to go into details about Life 365. But what I'm showing there is we left some of these concrete cylinders in chloride solutions for 2 years, for 5 years, for 15 years, and profiled them and looked at the data. I'm only showing the 2 and the 15-year experimental data there because the 5-year data, which is the green line, just mixes things up too badly. But the curves there are the predictions from Life 365, and the points are the actual real data values. So you can see Life 365 gives you a pretty good estimation of what's really going to happen. Just to be fair to slag, shortly after this, the CN rail tunnel was built, there was an extension built to the TTC, the Toronto Transit Commission, the subway system in Toronto. And in this case here, they used a ternary blend with silica fume and slag. In this case, they actually used a blended silica fume cement with about 7.5% silica fume in the cement, and they blended that at the concrete mixer with slag. And again, we saw a diffusion coefficient actually in the specification. You might notice on the last slide, I forgot to point it out on the last, there was also a permeability specification as well for the CN rail tunnel. I actually showed it, the actual real data was a blank. You couldn't actually force water through this concrete, so we actually couldn't measure the permeability. It was essentially, within the duration of a test, it was impermeable. We couldn't actually make water flow through the sample. We do have some data from Treat Island. With ternary mixes, only a little bit of data. For those of you who don't know, Treat Island is an exposure site. There's a wharf at the mid-tide level. It's an exposure site that's owned by the U.S. Corps of Engineers. Highest tides in the world is a 20-foot tide difference, daily tide difference, so it's a really very aggressive condition, about 100 freeze-thaw cycles per year as well. Over the past 60 years or so, literally hundreds of different programs put concrete on the site to sort of study marine performance. I just wanted to show you in the 90s, and since this presentation goes back to the 90s, this is relevant, there was some discussion about the role of air entrainment in high-performance concrete. People were saying if you had really high-performance concrete, 0.33 water-cement ratio with silica fume, you didn't need air, right? I don't know if people remember that, but there was a great deal of debate. Well, that's what happened to the non-air entrained high-performance concrete at Treat Island. It's not there anymore. This is some pervious concrete that was placed at Treat Island 2 years before I took the photograph. So I know pervious concrete is not designed to be in the marine environment with 100 freeze-thaw cycles a year, but if you are foolish enough to use it in that application, that's what it will look like. You can see here, there's a little piece left. We're actually subjecting that to very extensive microscopic investigations at the moment. I'm going to have a PhD thesis very shortly on that little piece there. CanMet started to put blocks out there in 1978, I think. And in 2003, we started to bring samples of these back as they hit an age of 25 years, and I'm sure people in the audience have heard me present on this before. I'm just going to present some stuff on the ternary mixes. Really a very extensive use of SCMs. They used high levels of fly ash, high levels of slag. There was high-volume fly ash concrete out there, silica fume concrete. Unfortunately, only really one example of a ternary blend, and that's all I'm going to show here. In 1985, they put out a ternary blend with silica fume and fly ash. We brought it back when it reached 25 years of age, so 2010. And you can see there's actually the data points there are the chloride profiles in those blocks at 25 years. And there, the curve there is Life 365's prediction. So again, Life 365 is actually a really good indicator of what happens under marine conditions. It's not so good for highway structures, I will add that, but marine exposure is pretty good. Just another example of use of Life 365. These are some silica fume concrete blocks that are in the Trondheim Fjord in Norway. They've been out there over 20 years now, and we actually use Life 365 again to predict the experimental profiles. And I'll just draw your attention to the latest age data, 21 years. The Life 365 pretty much nails the profile very accurately. So again, for marine exposure, Li 365 really is a good indicator of chloride ingress. In Canada 10 years ago, there were two ternary cements being produced at the time, one with fly ash and one with slag, and both with silica fume. Again, taking advantage of the silica fume, giving you early age performance, with slag and the fly ash filling in later on and giving you later age performance. The slides I'm going to show you is from an experiment that we did in Picton, Ontario, at the Esrock cement plant. This was a really good collaboration. It involved all 4 cement companies that were operating in Ontario at the time. Esrock provided the site, Lafarge provided the cement, St. Lawrence provided the concrete, and Blue Circle provided the Kentucky Fried Chicken that we had for lunch, if I remember correctly. We put a whole series of slabs in there in 1998. I'll show you the details of some of the mixes. This is all trafficked concrete. It's trafficked by cement trucks every day. Frequent applications of de-icing salt. So we were interested in both the de-icing salt durability and also ASR. We deliberately used a highly reactive aggregate in this concrete. Some of the details are a relatively high alkali cement. We used a blended type 10 silica fume cement with 8% silica fume in it, and we used slag added at the mix as second ingredient. The aggregate we used was a Spratt aggregate. I think anybody who's done any work on ASR has probably worked with this aggregate one time or another. It's kind of a standard reactive aggregate that's used worldwide. It's considered to be a highly reactive aggregate, so it's not very high. We now have a new category, very highly reactive. It's on the borderline of being very highly reactive, but it is a reactive aggregate. These are the mixes that we use. So we had a control mix, a mix with just a binary mix of 8% silica fume. And then we had mixes with just binary mixes with just straight slag, 35 and 50%, and then 3 ternary mixes, as you can see there, with between 4 to 6% silica fume and 25 to 35% slag. All of these concretes were cast in. Obviously, we produced the slabs in the field, but we also produced laboratory samples for laboratory tests at the same time. The scaling slabs were, I was going to say they were finished by the same contractor who finished the slabs in the field, but actually you can see Doug finishing that one there, so I'm not sure that's actually the case. That's probably the one that scaled really bad. We've been back various times to take cores out of this site as well, and fairly recently I think we had a paper at the last ICAR, the last AAR conference, on the performance of some of this concrete, so I'm not going to get into too much detail. The slabs were placed and finished using a vibrating screed. A curing compound was applied as well. And I think you can see here the curing compound being applied really nicely, nice and uniformly. The one thing I learned about this site is the most important piece of equipment to have on site to ensure quality control is a video camera. If a contractor knows he's being videoed, he'll do everything correctly. So we have really nice application of the curing membrane there. Just to show you some of the data, these are 3D plots, the yellow bars of the ternary mixes there. You can see with the straight binary mixes with just slag, we're seeing a little bit of a reduction in strength at 28 days. But in the ternary mixes, the silica fume is really helping us compensate for that, some of that early age strength loss. These are rapid chloride permeability results. You can see a straight silica fume mix is performing very well, but so too are the ternary mixes as well, the yellow bars here. These are with just straight slag. They did catch up eventually. These are 28-day results. At 28 days, you don't expect too much of a decrease because of the use of slag. You'll see it much more at 56 days and 90 days, but at 28 days, the ternary mix is performing very well. We also did chloride diffusion testing using what's now the 1556 test. At the time, there wasn't a standard test method. Well, there was actually the Nord test version of that. That's what we used. So I'll show you a couple of chloride profiles there. This is a 2-year profile of chlorides. You can see the benefits of adding slag there. These are straight slag mixes with 35 and 50%. So in every case, I'm showing you the straight cement mix there, the type 10 cement. Type 10 is the same as type 1 cement. It's a type GU cement, whatever terminology you prefer. That shows the blended silica fume cement. And if we superimpose the ternary blends on there, you can see the ternary blends are really giving us much, much better performance than a straight silica fume mix. And better performance than a straight slag mix as well. So the ternary blend really is providing us excellent resistance to chloride ion penetration. And they're just the calculated diffusion coefficients. You can see these are the 3 ternary mixes here. And you can see, although all of the numbers are low for anything with a blended cement, you can see that everything's at least 4 times lower than the straight Portland cement value here. You can see the ternary systems are really, they're 10 times lower than the straight Portland cement mixes. Where we didn't see great performance was in the scaling. We did cast miniature slabs from these concrete mixes for a de-ice salt scaling test. And you can see here that at 50% slag, we really saw very, very aggressive scaling. That's at 50% slag then, a binary mix of 50% slag. Pretty much looks like my driveway before my wife overlaid it with asphalt. Well, she didn't do it. She got a contractor to do it. But in the field, we really aren't seeing, we are seeing a little bit of maybe some coarse aggregates being exposed, but in general, the field performance is not really mirroring what we're seeing in the lab at all. I think Jan made the point, somebody else made the point before this week. The de-isosalt scaling test is really very, very severe, especially for concrete that contains blended cement. And especially if you follow the curing procedure, which is 14 days wet curing, followed by 14 days drying. That surface strength with 14 days wet curing, you're not going to get anywhere near equivalent performance when you have 50% slag in there. So it's a very aggressive test. We really don't see that poor performance being shown in the field. And you can see there with the Ternary cement, we are seeing some coarse aggregate exposure, but it's really not much worse than the control. These are heavy use of salt on these slabs, a heavy truck traffic, so we are seeing some abrasion, some surface loss, but it really isn't very severe. ASR performance, we cast prisms from this concrete and ran the 1293 test. You can see that 35% or 50% slag did very well. Silica fume was borderline. It just failed the test at 2 years, and the Ternary mixes gave us the best performance at all. We have been back now. This site now is close to 20 years old. Doug and I were discussing we might go there this summer, take a look at them again. The last time I looked, only the control mix was showing any kind of surface cracking or deterioration. So all of the blended cements have worked up to about 15 years. Obviously, time will tell if they'll be effective very long term. And that just shows the expansion. I like these ternary pots. So you can see there the expansion of a ternary mix is by far the lowest of all of the blended cement mixes that we actually used. And that just shows the control mix at about 5 years. It was just starting to show cracking at 5 years. We have conducted testing with other ternary mixes that don't contain silica fume. This is just showing some data for fly ash and slag mixes. Fly ash and slag, believe it or not, also have a synergistic effect. Fly ash is a pozzolan, slag isn't. Slag's a latent hydraulic material, so you're not consuming, there's no competition for the calcium hydroxide. The fly ash will react with the calcium hydroxide, and the fly ash just sits there and does its own thing. We really get excellent performance in ternary blends with fly ash and slag without silica fume, but maybe I shouldn't mention that at this meeting. All the data I've showed you up until now has mainly been for silica fume and slag. We've done a lot of testing with silica fume, blended silica fume cement with various levels of fly ash, including very high levels of fly ash here. All of these mixes are made with blended silica fume cement, so the cementitious type 10 SF component here contains 7.5 to 8% silica fume, and you can see up to 56% fly ash. These concretes give us really excellent performance. We have chloride diffusion data for these as well. What I am showing here is rapid chloride permeability data up to 5 years. So this is a mixture with about 3 to 4% silica fume and 56% fly ash. The rapid chloride number for this was 16 coulombs. There's an average of 2 test results. One was 32, one was 0. We're actually making concrete that is essentially electrically resistant. I mean, it really is a very, very high level of chloride resistance. I think we can actually make concrete nowadays that is totally chloride resistant. We just have to stop it cracking. That's the next challenge, right? And in fact, I did say that 10 years ago when I showed this data last. So we still haven't got there to make crack-resistant concrete. Just showing the data in a different way here. So you can see everything with fly ash, we're below 100 coulombs. This is the type 10 SF cement, so it has 7.5 to 8% silica fume and no fly ash. And you can see that with age, it really doesn't get any better. With silica fume, you get what you're going to get at 28 days. And you really don't see much improvement with age. But if you put fly ash in there, you can see with age, you really are getting this long-term benefit that does count. You don't have to have all your durability at 28 days. You really can wait for some of this stuff to happen. What about optimization? Just a couple of slides here. How do you optimize a mix? And Jan was showing some slides about optimizing. It really depends what you're optimizing for. If you want to optimize at 28 days, you're probably going to come out with putting no fly ash in there, maybe just silica fume. So it really depends where you optimize, and just showing you some examples. These are just showing response surfaces for mixtures with silica fume and fly ash. And if all you're interested in is 28-day strength, then yeah, 8% silica fume is your answer. If you want to get into long-term properties and look at 1 year strength, then you're going to see the ternary blend is going to be better for you. You're going to get much better strength. You can see here that if you're interested in the 1 year rapid chloride permeability test, again, you're going to get the best results of the ternary blend. If, however, you look at a 28-day result, you're probably not going to use fly ash. If you want to look at a 1 year result, if you really are interested long-term, then you're going to see the benefits of the fly ash really kick in. The ternary blend long-term gives you much, much better performance. So my conclusions, and this is more than 10 years old, cement's not great when it's straight, but it's splendid when it's blended. So I'll leave you with that. Thank you.